We're going to continue on here, still chapter 14 for the last time, probably. We're in the middle of this titration problem. So I think last time we did A and B, if I'm not mistaken. So we have C and D to go. So we'll just kind of pick it up from there. We talked about last time, obviously here we have a Ka value. So again, this is a titration of a weak acid with a strong base. And again, we should have our titration curve looking like so. I think we started here and then sort of rose to here. So now the next spot we're going to go is the equivalence point. And in this case, we are titrating 100 milliliters of 0.1 nitrous acid with 0.1 molar sodium hydroxide. So again, here our sodium hydroxide up in the burette. And obviously here we are adding to our acid on the bottom there. All right, so we're at the equivalence point. So let's take a look at that there, I think, which is C. And again, we have 100 milliliters. 100 milliliters of 0.1 molar nitrous acid with 0.1 molar sodium hydroxide and a Ka value of 4.5 to the minus 4. All right, so at this point, obviously we are adding, so we do need to do an ice table like we've been doing in moles. Again, here they don't actually tell you the volume to reach the equivalence point, but you will need to know that. So once again, you could find it a couple different ways. You can, in this case, because it's a one-to-one relationship between the acid and the base, you could use M1V1 equals N2V2. And if you do that, you'll end up with the volume needed to reach there. And in this case, it would be 100 milliliters. As you got 100 milliliters, 0.1 molar V2, divide that over, and you will end up with 100 milliliters to reach the equivalence point. So we can do our reaction here, which is going to be our sodium hydroxide, which is what we are adding. We're going to react it with our nitrous acid, which is what we're starting with. And again, we're going to get sodium nitrite and a little bit of water happening here. We obviously here, like we've been doing, need to do this in moles. So at this point, we'll take 0.1 times 0.1, which is our volume converted to liters, times the molarity, and that will give us initially here for our HNO2, 0.01 moles. Once again, if by some chance you couldn't remember this, you could also, as I mentioned, figure out the volume to get there by knowing that at the equivalence point, we should have the exact same number of moles here of sodium hydroxide. So that is what the equivalence point means. And since we do have the molarity here, thank you, which is here, moles per liter, and we know the moles, we could also just use the molarity equation and figure out the 100 milliliters that way as well. So again, there are a few different ways you can kind of get there. This is going to be 0. Since we are at the equivalence point here, we cannot hopefully pick the wrong number. It should really be the same number there. So we're going to go minus 0.01 plus 0.01 moles. That means when we reach equilibrium, I'm going to have 0, 0, and 0.01 moles here. A question on the table. Now, the importance of obviously figuring out that volume to reach the equivalence point is for right here, because we do want to convert back into molarity. So we want our total volume. So obviously here we started with 100 milliliters of the acid. We did our calculation here to figure out we also need to throw in there 100 milliliters of our base. That's going to give us a total volume at this point of 200 milliliters when we add it together. Obviously, we need to convert that to liters, so we're going to divide that by 1,000 or move the decimal, and that's going to get us here something in the ballpark of 0.05 molar. Any questions there? Once again, if you're not sure sort of what's happening here, although we should kind of know based on the titration we're doing and where we're at in the titration, but just in case you are not sure, we can look at our ice table. And really the only thing we got left at this point here is a salt. And we have the salt here that's left over. And remember that whenever you have sort of a salt involved or left over, the one thing you want to think about is whether or not it will go through hydrolysis. And in this case, that salt will go through hydrolysis, not the sodium part, as obviously that is group one, but the part here that actually comes from this weak acid. So because it comes from a weak acid, the NO2 minus part of the salt will go through hydrolysis, and that means that we will actually get a second ice table happening at this point, and that is basically a hydrolysis reaction between the NO2 minus and the water. Since it comes from a weak acid, it will act as a base here, and regardless of that, it does not have an H to give, so it can only accept in this case. So it will actually accept the H plus here along the way. And that is going to give us our hydrolysis reaction that's going to occur. And if I find me an arrow, there we go. It will make where it came from there, and it will produce hydroxide. So once again, as we do expect in this type of titration, the pH here at the equivalence point should be basic, as we have the salt going through hydrolysis is producing hydroxide and should make, again, that pH basic. All right, so what we need to do then is take our equilibrium value of our salts, and that's now going to come our initial concentration here. And remember, we're going to go 0, 0. This is now going to turn into an X type table here. So plus X, that means at equilibrium, 0.05 minus X, X, and X. Questions on that so far? Now, because this is basic and we did produce hydroxide here, we hope we should remember that in our calculation here, we do need to use a Kb value and not a Ka value, not the one that was given to us. So we do need to use that relationship of Kw. So the Kb in this case would equal our Kw divided by the Ka. And that's going to give us 1 times 10 to the minus 14 divided by, looks like 4.5 times 10 to the minus 4. That's going to get us here. If I punch the right numbers, it might get us something. Let me see. It's a lot of 2's. 2.2 times 10 to the minus 11. All right, so obviously here our equilibrium line is going to go into our Kb expression. I'm just going to flip the page here. So our Kb in this case is going to be the concentration of HNO2, OH minus divided by NO2 minus, and that's going to equal our, we got there 2.2 times 10 to the minus 11. Popping our values in there gets us an x squared, 0.05 minus x equals 2.2 times 10 to the minus 11 in this case. And obviously that is a small value of k, so we could do our assumption here and assume x is equal to 0, and that would then reduce this down to x squared divided by 0.05 equals 2.2 times 10 to the minus 11. We're going to multiply first and then do a little square root afterwards, and let's see what we get there. Do that, do a little bit of that, and we're going to get something with a lot of zeros. Let's see here. X is going to equal 2.1. I'll call it 08. I'll take a few digits times 10 to the minus 5. We again want to, bless you, make sure that we do check our value. So we do want to take this divided by 0.05, bless you, times 100%. So we'll take that divided by 0.05 times 100. That's going to give us 0.04%, which means the check here is good. So we do have our x values. So again, it's important maybe to reference your table, and hopefully you wrote your equation right. And when we come back to our table, once again here, that x is not the H plus concentration, but it is the OH minus concentration. So this is going to equal the OH minus concentration. So we get our POH here. So our POH will equal minus the log of 2.108 times 10 to the minus 5. And it's going to look like something here. Try that one. Looks like 4.68. pH then would be 14 minus that number. And that clearly is not basic, that first number. So this one is, though, 9.32 in this guy's, which is a basic pH, which again is what we should expect to happen here as we have that salt going through hydrolysis and producing hydroxide. Any questions on that part there? So remember, as we talked about before, again, if you kind of know where you are in the titration and you know what type of titration, you should expect, again, a hydrolysis type situation at this point. And again, sometimes it's a good thing to just take a moment and kind of think about what should happen, and it kind of helps you with the calculation sometimes. Any questions on that? All right, so now we are obviously up to here. So now we're going to roll past the equivalence point here, obviously, and we're going to figure out the pH for part D when we add 105 milliliters of our base. So let's take a look at that one there. So D is 105 milliliters of our 0.1 molar sodium hydroxide added to our 100 milliliters of our 0.1 molar nitrous acid. All right, so obviously in this case, still gonna get the same sort of reaction. So we're gonna go sodium hydroxide here, plus our nitrous acid. Going to make our sodium nitrite and our water. We're gonna get some moles here, and obviously again, this is what we're adding. This is what we're starting with. And at this point, we will have, it's like 0.105 moles. We'll have our same sort of starting amount here. And our 0. And as I think we've talked about previously in a problem like this, again, you can assume that each part is sort of separate from each other. They're not usually carrying on volumes or anything like that. So for each part of a problem like this, you just assume you start at 0 every time and kind of just add the amount for that part. Here, as we talked about, because we are definitely past the equivalence points, by the way, once again, I know that regardless of the fact that I had a problem before where I was at the equivalence point, I know that because when I compare the amount of base I'm adding is more moles than what I'm starting with over here. So again, that is what's going to tell me that we are past the equivalence point. And since we are past the equivalence point, we have kind of a switch. This again is going to be the excess reagent. This is going to now be our limiting reagent. And the change here does has to be the smaller number. Again, you cannot have negative numbers happening. And that's going to get me here 0.0105 minus 0.01, 0.0005. That's going to be 0 and 0.01 moles. At this point, we could get our total volume. So obviously here we had 105 we added. We started with 100, so we're looking at like 205 milliliters as our total volume. We're going to divide it by 0.205 liters. And we're going to get here one more. It's like 0.00244 and 0.01 divided by 0.205, 0.0488. So again, if you're not sure, you should take a look at your ice table and sort of figure out what you got going on. So obviously here we got some salt left over. We have some sodium hydroxide. Once again, a reminder that just because you got two numbers does not make it a buffer as much as you might want it to be. It is not a buffer here. Again, we basically have the salt that we were talking about at the equivalence point that will go through hydrolysis and act as a base. And we have here sodium hydroxide, which is a strong base. So as we talked about at this point in the titration, this guy here is going to be the major contributor. So we're going to ignore the contribution of the salt at this point. That means that this is really our hydroxide concentration. And that means we could go right into our POH in this case, 0.00244. And that's going to get us here. Looks like a 2.61. That obviously is a POH, so our pH would then be 14 minus that, like 1139, which definitely is basic. And again, what we would expect to happen since you've obviously past the equivalence point, you blew through all the acid you started with, and at this point, you're basically just dropping hydroxide into your beaker, and it's going to see a pretty high pH result as that. Any questions on that there? All right, questions on titrations. Yes. No? Okay, last little bit of 14. I can't believe it, the last bit. Let's see what we got left. All right, we're gonna talk a little bit about acid-base indicators. We've kind of been talking about it as we've been going through some of these examples, but a reminder again that acid-base indicators do work specifically over a pH range, and the idea of choosing a good indicator is one where you would see a change in color around the equivalence point is typically what you would want to choose. The idea there is to give you a visual representation of, hey, maybe you should stop your titration, you're near the end. And you can see on this list, for example, here, depending on the ratio of your protonated indicator, and indicators are kind of like weak acids, kind of like a protonated guy. It's got a hydrogen on it, and a deprotonated form of it where it kind of lost the hydrogen. And depending on the ratio of it, if the kind of protonated form is greater than kind of the deprotonated form, you'll see the color of the acid, and vice versa. If you have more of the kind of deprotonated form, you'll see the color of the base. So here you can see, for example, crystal violet, rolling kind of a bunch of colors, kind of yellow to green to blue. And it really does work over this sort of pH range here, kind of 0 to 2, which clearly would not be a great one if your equivalence point is basic, right? So you wouldn't want to choose that, nor would you probably want to do anything like creosol red, right? Because if your equivalence point, for example, is basic and you choose this guy, it's going to turn blue pretty early, and that's never going to change color again, and you will not know where your equivalence point is, right? Because it changed too soon. Um, and before this, even though it's not colored, this guy will kind of stay red from this point, and then it kind of stays that color after that point. Um, and again, you can see, depending on what you want, you're kind of moving a little bit more acidic sort of a range, heading to kind of a neutralish, basic type of range. There's our favorite one right there, which is phenolphthalein, as we talk about again, colorless to that pink. So when you're choosing, like I said, an indicator, you definitely want to choose one that you'll see that noticeable change. You also could, for example, do a theoretical calculation on your titration and maybe really pick one that's super appropriate based on what you think it should end up in terms of the equivalence point. Just like phenolphthalein is used a lot, it would be a really crappy one, right? For one where the equivalence point is acidic, right? because it's just going to be colorless as soon as it hits around a pH of 8, and you'll never be able to know when it changes, right? So again, you do want to choose one that works in the appropriate range of your equivalence point so you see the color. So with that being said, here is another chart of some indicators. Which ones on here would be good for this titration of HNO2 and potassium hydroxide? Take a moment, choose which ones might be a good choice here. Okay, so let's take a look. Obviously, it's the one we actually just did in that example. So we know that this is a weak acid. This is a strong base. And because that is a weak acid, strong base, right, we're going to have our little titration curve looking like this. Our equivalence point should actually be, as we just calculated, basic, right? I think in our particular example, it was 9.3-ish. So it's definitely basic. That pretty much eliminates these guys here in terms of being any good. Although the last one does get into 7.6, that's not very basic, right? And by then it probably has changed color, so it's probably not your best choice. So if you had to choose, probably these two at the bottom might be good. And if we were doing specifically the one we were just calculating, probably phenolphthalein is a little bit better. You have a little bit more room there. But these two are definitely basic. You see some type of color change as it gets basic. And so probably the creosol red or the phenolphthalein would be your two best choices for this type of titration. So again, like I said, if you were doing some type of weak base with a strong acid titration where you would expect the equivalence point to be acidic, one of these guys might be a much better choice. And like I said, you could do some type of theoretical calculation to determine approximately where you expect the equivalence point to be. Any questions on that there? Yeah. Right. So we talked about kind of three types of titrations, which is strong acid, strong base, where because at the equivalence point you basically have a neutral salt, the pH should be 7, right? The one like we just did in that example, or in this example here, is a weak acid and a weak base, our weak acid and a strong base, because of the salt that's there at the equivalence point, will produce hydroxide. We would expect it to be basic at the equivalence point. So we definitely would want an indicator to change its color in the basic range, as opposed to our weak base and strong acid, where the salt will actually produce H plus or H3O plus, and we expect it to be more acidic, and we would want one that would change in a more acidic sort of range and stuff like that. So it is based on really the equivalence point, because typically if you're choosing an indicator, unlike the titrations we'll do, but you typically, like you did in Chem 50, you use an indicator to tell you to stop your titration right at the equivalence point or as near to the equivalence point as you could get. And that's why you would want to choose one that kind of changes color near where you would expect it to be. Other questions? Okay. That does wrap up, I believe, chapter 14. Never thought it would end. After 14 comes 15, so we're now dropping downward here on our roller coaster of fun stuff. So chapter 15 is not too long of a chapter, and it involves a couple of other types of equilibrium constants, and that is KSP, which is the solubility product, and KF, which is the formation constant. One involves, as you might imagine, solubility, and one involves basically complex ion formation. And they are sort of different, and we are going to talk about KSP first, and then we'll get into our sort of KF here. So starting with KSP, KSP is the equilibrium constant really for things that are insoluble. So when you think about your sort of solubility rules that you learned or saw or could find in a table, I suppose. There are certain things that when they come together are classified as being insoluble and that you should expect a solid to actually form. One of the things we will see in this chapter is that's not always the case. There is actually a lot of factors to determine, for example, whether or not you'll actually see that solid form. So even though solubility rules say if you put these two things together, you should get a solid, there are a lot of factors that we'll talk about in this chapter that may affect whether or not you actually see that. Things like pH, things like the concentration of everybody is a really important factor. Now, another concept that sometimes people have a hard time sort of grasping is the idea that um, even things that are insoluble will pretty much break apart a little bit in solution. They don't break apart a lot usually, but they mainly stay together. But there is a little bit of it that will break apart into the ions and set up an equilibrium. So if we take something like silver chloride, if you remember your solubility rules, things like chlorides, bromides, and iodides are soluble in everything except silver, lead, and mercury 1, lead 2, and mercury 1. And this is an exception, which means it is typically insoluble. This is a white solid that you've probably seen along the way there in Chem 50 on a lot of those chemical reaction type of experiments. And this is a precipitate that will form. So even though we consider silver chloride to be insoluble in solution, a little bit of it will break apart into its ions and set up this equilibrium. And because it does set up an equilibrium, we could write an equilibrium constant for it, which is the same as normal, which is our products. Oops, so our products over our reactants. And in this case, it would be the concentration of silver times the concentration of chloride equals our KSP, which again is our solubility product. One of the, I guess, nice things about this type of equilibrium is, for the most part, this is always how these reactions are written. You have your solid guy on the left and your aqueous ions on the right. So you always kind of have solid on the left, aqueous ions on the right. And because of that, when you write the equilibrium expression for it or the KSP expression, frankly, it is just products that get involved. So because reactants are typically always solid, so you never have to put them in. So it's really just kind of products. And we do the exact same thing we do on any other equilibrium expression because they're all really the same, regardless of the little letter on the bottom. We do still take the coefficients as the exponents. So if you had some type of ionic compound like magnesium fluoride, again, would break apart into magnesium and two fluorides. So if we wrote the KSP expression for this, just like we normally do, we take those coefficients into account and also obviously include them here in our expression. If you got something like silver carbonate, we get a couple of silvers and one carbonate, which again gets incorporated obviously into our expression. And we would have the concentration of silver times the concentration of carbonate. Calcium phosphate, we've got both of them have some coefficients. So they both get basically included in there. Again, calcium's concentration to the third power times phosphate's concentration squared. Now, there is one thing that we oftentimes will sometimes look at to help us decide whether or not, for example, a solid would form. So if we put these two things together and we want to determine whether or not we would expect a precipitate to form, one of the things that we look at is Q. And that Q is the same Q that we talked about in the equilibrium chapter and some other places as well. It is calculated the same in this case as KSP. So Q is calculated the same as the KSP. So for example, if I wanted to calculate Q for this one, Q would be the concentration of silver times concentration chloride, basically. So again, just calculate the same way. If you do that and Q is less than the KSP value, then you have an unsaturated solution. And if you have an unsaturated solution, that means that you would not expect a precipitate to form. So if you calculate Q and it equals the KSP value, you have a saturated solution. And if you don't remember what a saturated solution is, that is the point where you have basically dissolved as much solid as you can at that given temperature. And if you put any more solid in there, it will not dissolve. So it's kind of like at the point, the exact point where you're pretty much going to start to see a precipitate form if you continue your process there. If you calculate Q and it's greater than the KSP, then it's going to make a supersaturated solution. And in a supersaturated solution, it basically means you have too much solute for that solvent, and you would expect a solid definitely to form. So if you kind of do Q on the left there and KSP on the right, basically just go opposite of where that thing is pointing, will tell you. So it's pointing to the left, we go opposites, and this way is ion, so it should be soluble, no precipitate. This guy is pointing to the right, opposite is to the left. So going this way, you would expect a solid to form. So kind of opposite there is what we typically see. Now, these are some values from your book there of KSP values. And one of the things that you will actually see in KSP values is they are typically very small. So these are typically very small values. For example, if we just kind of pick some out here to the minus 26, minus 22, minus 20, minus 45. So these are very, very small values. And that makes sense based on the idea that this is basically an equilibrium constant for things that are insoluble. So if you think again a way the reactions are written where we have solid to aqueous ions, if you have a small value of K, that means at equilibrium you mainly have reactants, right, with a small value of K. And that means that mainly this thing is going to stay together and not break apart, which is sort of what the solubility rules say it should do. Basically stay together and make that solid as well. So these guys typically are kind of on one end of the spectrum, which is the typically very small values of K, sort of end of the spectrum. And again, may have to refer to this table to find some KSP type of problems or values. Now, when we have solubility type problems or KSP problems, there's kind of two sort of problems or ways that we sort of work these problems. One for sure you should do an ice table. The other one, it probably wouldn't hurt to do an ice table. But we do end up looking sometimes for two types of solubility. One is what is referred to as the molar solubility. And the molar solubility is a fancy way of saying the molarity, right? So moles per liter. So you're basically looking for the molarity of something. And that is the number of moles of solute that can dissolve in 1 liter of a saturated solution. And sometimes we just look for the regular old solubility, which are grams per liter, and that's how many grams you could get to dissolve of a solute in a saturated solution. Now, if I have moles per liter and I have to go to grams per liter, what is the thing that sort of ties those things together, allows me to do that? That is the molar mass. Yeah, so if I take the molar mass, which is grams per mole, and slip it in there, and we multiply everybody, the moles will cancel, and we'll end up with grams per liter, right? So if you have the molarity and you want to go to grams per liter, it's the molar mass to do so. And vice versa, if you have the grams per liter and want the molarity, you're going to divide it right out by the molar mass. So that molar mass is sometimes used here to get to the molar solubility or the solubility of a product. All right, so two types of problems typically is if you are given the solubility of a compound, you can take that solubility of it and convert it into the molarity of the compound, and from the molarity, you can figure out the concentrations of the ions that are present, and then you could go into the KSP expression and solve for the KSP. Now, if you're actually given the KSP, and that's kind of the only thing given to you, probably an ice table definitely should be rolled out for that. And really, you could also use an ice table in this case. But in this case, you do kind of an ice table. You would solve for your unknown, And when you do, that is going to give you the molar solubility of your compound. So let's take a look at one here. What is the solubility of silver phosphate? I'm not sure why the big pause there on the silver phosphate formula for dramatic purposes. At 25 degrees is 1.6 times 10 to the minus 5 moles per liter. We're actually looking for the KSP in this case. So in this particular case, you might not have to actually do an ice table if you understand some things about molarity and concentrations. But I'm going to show you the ice table, so kind of show you how we do these ice tables. And they're just slightly different than a normal sort of table in a sense. So if we were going to kind of take an ice table approach here, we're going to start with our silver phosphate. And by the way, one of the things that's really helpful in this chapter is knowing your solubility rules. But frankly, if you don't know your solubility rules, uh, and you're asked to find the KSP or you're given a KSP, you can pretty much assume that thing's going to be a solid to start with. So even if you maybe don't know all your solubility rules, you can pretty much figure it out. If there's a KSP involved, somebody's going to be the solid. This is going to break apart into 3 silver ions and a phosphate ion in this case. And this will give us our KSP expression. That will be our silver that we will need to cube because of the coefficient, and times our phosphate in this case. And obviously that is actually what we're looking to find, which is what is this value? All right, so we're going to do an ice table here. And frankly, because the guy on the left here is a solid, do we normally worry about solids or anything like that in equilibrium? We don't, so much just leave it alone in the sense. So we're not going to really do much with that. So we're just going to kind of go to the other side, and we're going to start with zeros, basically. And it's safe to assume that zeros, unless there's some other information that tells you not. Now, normally, right, we go minuses on the left and pluses on the right, and we still do that in this case. So a little bit of it's going to be made on the right. This will be plus 3. Again, we do need to take the coefficient. Now, a slightly different than a normalized table is typically people, when they do this calculation, they actually don't use X, they use S here. So this would be plus 3S, and this would be plus S. So what does the S represent? The S represents, in this case, the molar solubility. And that's basically the molarity. You want to still roll with X's, it comes out the same as whichever letter you want, but typically people will still kind of use S's here. This is going to come down to our equilibrium here, and this is going to give us 3S and S in this case. First off, any questions on that there? Now, if you did have the KSP, this would be kind of the ice table that you would do, and you can't even do it here as in this type of problem. And you would obviously go into your KSP expression. So we would take our equilibrium line here and come into our KSP expression, and that would get us 3s cubed times s equals our KSP in this case. Now, again, if you had the KSP given to you, you would solve for S, and that would give you your molar solubility and probably the answer you're looking for. But in this case, we are looking for the KSP. So if we take a look at the other piece of information that was given to us, which is the solubility of this guy is 1.6 times 10 to the minus 5 molar. That is, by the way, the molar solubility in this case, right? Because it's the molarity here. And that means that we basically just need to pop into here our S value in this case. And that would give us 3 times 1.6 times 10 to the minus 5 cubed times 1.6 times 10 to the minus 5. And that will get us 3 times 1.6 to the minus 5. And again, we're going to cube it if we can find that button. There it is. Try that one. We're going to times it by 1.6 to the minus 5. It's going to give us a KSP here of 1.8 times 10 to the minus 18 in this case. first off, any questions on that there? Now, why would I recommend to still do the ice table, even though technically you might not need to do it on this particular problem? The reason is it is very, very common when people work on these type of problems is in their head they go like, oh, I put a 3 here, I don't need to put a 3 here, right? Or I put a 3 here, I probably don't need to do the 3 there. So again, you can just visually see that you do need to have those 3s in both locations if we kind of run through the ice table. And that's a very common sort of error people make, is that kind of like they feel like they've already done it, kind of used the coefficient already, and they don't have to use it again. So visually, it sort of helps you sort of see that you should do that. Now, when I say you don't maybe have to do an ice table, if you understand molarity, basically you could take, and it's really what the ice table is doing, but you know, this obviously breaks apart into this guy here. And since we have the concentration of this guy, as we might have talked about with concentration, it's a 1 to 3 relationship. So you would take 3 times the 1.6 times 10 to the minus 5. That's a 1 to 1 relationship, which gives you 1.6 times 10 to the minus 5. And then obviously you can take these guys like we just did there. But that's basically what the ice table is doing for you, is kind of doing that for you and putting it into there. Yeah. You could, you should ideally come out probably the same if you put the S in there, but there's no necessary need to perhaps do that, but it should come out the same. Other question? And you would do that, by the way, if you did have the KSP and you needed to solve for S, you definitely would want to put it together like that so you could get that 27 divided out and then take the fourth root of it in that case, yeah. Other questions? Okay. All right, so why don't you try this one? What is the solubility in grams per liter of silver chloride, the KSP there of silver chloride 1.6 times 10 to the minus 10. Silver is, what's that, 107.9 perhaps grams per mole. And chlorine, 3545. So again, even if you didn't know your solubility rules, you should know silver chloride here would then be a solid. So we will have silver and chloride it would break apart into. This would give us a KSP expression of basically our products, which is silver times our chloride, and this equals our 1.6 times 10 to the minus 10. In this case, we would do an ice table. So we'll go initially here 0, 0, change plus S and plus S. That means at equilibrium here, we got S and S. Any questions on the table there? This is going to go into our KSP expression here, and that's going to give us S squared is equal to 1.6 times 10 to the minus 10. Going to do a little square root there on both sides, I think. And this will get us here 1.6 to the minus 10. Gets us a 0.00001269. This is the molar solubility, moles per liter here. Not a lot of rounding at this point, but I'll just take the whole number since I have it. And this would be our molar solubility of silver chloride at this case. Obviously, you would want to reduce it down if you're going to give the molar solubility, maybe down to 0.00013 or something like that. Would be much better. But in this case, we're actually looking for grams per liter. And we would need the molar mass here of silver chloride. So again, that's 107.9 for our silver, plus 3545 there for our chlorine. It's going to give us a molar mass here, whoops, of about 143.35 grams per mole. Again, we're going to use that to convert, and we're going to multiply in this case by the 143.35 grams per mole. That's going to get rid of our moles and leave us grams per liter. And that's going to get us here a whopping 0.0018 grams per liter is the solubility of silver chloride in this case. Is that a lot? That is not a lot. That basically means you could dissolve approximately 0.002 grams of silver chloride in 1,000 milliliters of water. That's not very much at all, yeah? And that's why we typically think of silver chloride as being insoluble, obviously, because under normal conditions, that's about all that you could get to basically come out into solution and dissolve. Any questions on that there? Now, a couple of things you may be thinking, isn't S our concentration over here? And this S value that we got is definitely these S values here. So if we wanted the concentration of chloride ions in that solution, it would be 0.000013. And if we wanted silver's concentration, our ions, it would also be the same number. Now, typically speaking, when you do solve for S in these tables, it is the molar solubility of the whole thing together. And again, if you just did sort of backwards sort of relationship, if you know this guy is a 1-to-1 relationship, then it would be the same number going backwards and stuff like that. So typically when you do solve for that S, it is the molar solubility of the whole thing together, and also can be put back into the ice table like normal on the bottom there to help you get the concentration of your ions as well. Yeah. Any questions on that there? All right, let's try maybe another one here. What is the concentration of aluminum in an aluminum hydroxide solution? The 3 over there, maybe. Solution has a KSP of 2 times 10 to the minus 32. So give it a go, see what you come up with. Concentration of aluminum. So we're looking for the molarity basically. And we do have a KSP given to us, so we do know that that's solid. So we'll set up our sort of ice table here. And this guy is going to break apart into an aluminum. And we will get 3 hydroxides in this case. And our KSP in this case would be the concentration of aluminum times concentration of hydroxide, which we do need to cube. And that would equal 2 times 10 to the minus 32 in this case. So doing our ice table here, we're going to get 0 and 0. Change going to be plus S. Once again here, plus 3S for our coefficient. That means we're going to end up here with an S and a 3S in this case. Any questions on that? We do have the KSP value given to us, so we're going to take our equilibrium line here and we're going to put it back into our KSP expression. And that would get us S times 3S cubed will equal 2 times 10 to the minus 32. And this is going to end up with 27S to the 4th is equal to 2 times 10 to the minus 32nd. Remember, very commonly missed by a lot of people when they do this is they will cube the S and forget all about the actual number. So you do want to make sure you get the number there. Super common error people will do. Here we're going to, I think, divide there by the 27, then come back and take the 4th root of that. And if we do that, 2 times 10 to the minus 32 divided by 27, that basically give us S to the 4th is equal to 7.407 times 10 to the minus 34. Again, we're going to take the 4th root there of each side. And that is going to get us here. Yeah, do it this way. 1 divided by 4 seems good. That is too many zeros to look at. So that's going to give us an S of 5.2 times 10 to the minus 9. Or you may just have all zeros and a 5 at the end if you ran out of room on your calculator. That is going to be our aluminum concentration. As we can see from our table, that is what S is equal to. So the concentration of aluminum in this case would be 5.2 times 10 to the minus 9 molar. We could, if we wanted to, by the way, also figure out the concentration of hydroxide. That would be 3 times our 5.2 times 10 to the minus 9. And that would get us something like, maybe we'll call it 1.6 times 10 to the minus 8 molar. First off, any questions on that there? By the way, if we were curious about the pH of this solution, we could also figure that out as well, because now we have the hydroxide. That would allow us to get to the pOH, which if you put it in there, I think it's like 7.81. And then you can get to the pH after that, which in this case means this solution is hanging out around a pH of 6.19 in this case. So with this solubility, if you actually have something like hydroxide or H plus or H3O plus, you can still figure out something like the pH of the solution as well. Obviously, as well, if we wanted to know the molar solubility of the whole thing, it would also be this number here. And it works the same because, again, it's a 1-to-1 relationship between these guys, or it's a 3-to-1 relationship, which means you would take your concentration here and divide it by 3, which puts you back to the S value as well. So it all kind of works out the same. Any questions on that there? All right, we would lay it up there for today, I think.